Welcome back. As promised, I'm going to walk through a second example now. So we'll get rid of this. We're going to keep with the same idea of um, the table list Atwood machine, I will call it, because I think that's kind of the terminology that we've been using in class. This is the hanging style. I have mass 1, I have mass 2. Just to recap us, we have tension, I have weight 1, and I have weight 2. I want to go into kind of what I was asking you to think about with the study guide, which was very, very out of the box, very critical thinking oriented, which would be designing your own problem that's solving for a different variable than what we've been doing so far. So far, we've solved this exact system for acceleration. When we did the table oriented one, right, we had the Atwood machine on the table, we had the pulley, and we had mass down here. We solved for F mu, and I think that was it actually. And so these are the two things that we solve for in these types of problems. But I want to go kind of a step further and see what else we can solve for. So I wanted to throw you guys an example that you probably would never think to do. And hopefully if you guys worked with the study guide, you didn't take this approach. So I want to put this system on let's say Mars, and I want to essentially work this problem backwards, like I'm the teacher and hey, it helps that I am. But in the study guide, you guys are supposed to kind of take on that role of being the teacher and designing a problem for somebody else to have to solve. So I guess how should I write this? We want the end result. We want to solve for gravity on Mars. And so that would be an awful way to write that, because we don't use capital G for gravity. There we go. How about that? So the first thing that we need to do in designing a problem with this is we need to know what the answer is supposed to be. Maybe you've never really thought about designing a problem before, from scratch, and how would you go about that? But it's kind of like a puzzle, right? You need to know what the end result needs to look like before you can design it. So in terms of problem design, we need to know what our answer is before we can, start and figure out what variables we're going to give you and what we're not. So I'm just going to pull up my phone real quick and find the exact gravity on Mars. I think it's like 3.77 something. Mars gravity. That was close. All right, so gravity on Mars is equal to 3.711 meters per second squared. And I hit a button, and there we go. Okay. So this needs to remain in the back of our minds as we go through this problem. Let's go ahead and kind of jump to a good starting point with our problem, because we already solved in the last video how to find the sum of forces. So let's just jump to that. And I know that my sum of forces here are equal to W2 minus W1, and this is equal to MA. And this will help us get on track for figuring out what we're going to have the audience or the students solve. And so we need to figure out, like, if we don't provide enough givens in this problem, then this problem becomes very tricky to solve for, right? And so if we take this to another step, right? So I have my sum of forces equation, and we can also pull out that acceleration equation. And that was the G, blanking off the top of my head what it was. It's, is it M2 minus M1? Yes, we have 2 and 1 here. And then M1 plus M2. So thinking backwards, if we want the audience to solve for G, that G is going to end up being here, right? And so when designing the problem, we would need to tell the audience we have an Atwood machine on Mars. And automatically they should be thinking that G is not equal to 9.81 meters per second squared, because gravity on Mars is not that. And maybe they don't know exactly what Mars gravity is. I don't think it's something that we tend to memorize. So that helps, but we can obviously look it up so we can check our answer on the back end, which is nice. So you might ask yourself, okay, well, where do I start then? Like, how do I know what to provide the audience? So what I would say that we do is we provide the Atwood machine. And so we would draw the Atwood machine and say, here we go. We have mass 1 and we have mass 2. And I keep working with this assumption that mass 2 is larger. I'm just going to keep that up. So we can allocate whatever masses we would like to. We now need to make sure that we set up a problem where the gravity is actually 3.711. And to do that, we can choose masses and then we can solve for the acceleration that would have to be true if it were on Mars. So let me walk you through that if you were kind of confused about what I was just saying. So I'm just going to block off some work room here. I'm just going to, well, how about we go off of the last problem? We'll say that mass 1 is equal to 500 grams and mass 2 is equal to 1,000 grams. So this is 0.5 kilograms. This is, joke's on me, this is 1.0 kilograms. Cool. Any questions? That's a good joke, so I can't answer your questions. Okay. So I think the direction I want to go here. So I'm kind of keeping this running tab on the right here of things that I'm telling my audience. And so I would be telling them this. I would say that M1 is equal to 500 grams and M2 is equal to 1,000 grams. And then in this space here, I'm just kind of working out what I'm doing literally in this moment. So everything over here to the right would be what we're going to be preparing for the audience. So maybe we would be typing this up simultaneously like in a test document so that we were kind of keeping track of that as well. I'm just kind of doing it all on one screen. So working this backwards, we're actually pretty close to being finished here. We need to know one more variable to figure out G, right? For the audience to be able to solve for gravity on Mars, and we can say that gravity on Mars is our unknown, because it is. We need to provide one more known, and that would have to be acceleration. So to do that, I'm going to go ahead and solve this system for what it would need to be if G is in fact the 3.711 value. And I'm going to omit my units. So for everybody watching this that says that guy didn't track his units, I'm telling you right now, I'm omitting my units just to save my awful handwriting. And you see me do this in class all the time. And then I tell you don't do it. It's like when your parents tell you not to do what they do, even though they do it. Okay, so this is a decimal point, not a comma. So M2 minus M1, so I have 1 minus 0.5, 12 kilograms, of course, and now underneath I'm going to have 1 plus 0.5. Pull up the calculator here. Oh, my batteries are low. Of course they are. Cool. So I get an acceleration rate. I don't know why I wrote a 3. Literally, not even. Okay. And I'm going to actually just round it there. And so this would be 1.24 meters per second squared. This is the acceleration that we now have to give our audience to solve for this problem. So let's actually get rid of this here and add in this last known value, which would have to be acceleration of 1.24 meters per second squared. And then we would be asking them, okay, we want to find gravity on Mars. Or better yet, we could just tell them to solve for gravity and figure out what planet it must be on. We could kind of, make this puzzle or this a little bit more of a problem to solve. Instead of just saying, yeah, this is the gravity on Mars, we can have them seek that out. So let's recap, and I think I have enough room here. We're going to go back to our fun color from the last video to represent Friday the 13th. So let's now solve this problem to make sure that we did everything properly. And so to do this, I'm going to just start with my sum of forces equation and my acceleration equation, all this, because I've already demonstrated multiple times how we can find that. So in light of what I've been given in the problem, I know that my mass 1 is 0.5 kilograms, my mass 2 is 1 kilogram, my acceleration is 1.24 meters per second squared, and I'm solving for G. Remember the guess method. So my givens are here, my unknown is down here. Now I need to figure out what equation I'm going to use to figure this out. So I already know I have my sum of forces, and since I've solved that out, I'm just going to go ahead and pull the acceleration version down here. And so I have my acceleration is equal to g m2 minus m1, m1 plus m2. But I need to solve this for g, not a. So I'm going to go ahead and rework this to get g by itself. And I'm probably just going to do that all in one step here to save myself some space. So I'm going to have, it's basically just going to flip-flop this. I'm going to have a m1 plus m2 divided by m2 minus m1. And this is now equal to g. So this is going to be my new, let's see if I can do this. All right, this is going to be my new equation to solve for g. Take a moment to work out that math if you need to. Maybe pause the video. For those of you who are still with me, we're going to now just plug and chug. So I'm going to plug in my, see if I can kind of bring this down here and say g is equal to, and again, I'm omitting my unit, so don't want to hear about it. 1 plus 0.5 divided by, we have 1 minus 0.5. And let me put this in my calculator. I get an answer of 3.72 meters per second squared. You will recall we were going for 3.711. I would call this close enough. I would definitely call this close enough. Both of these round down to 3.7. A question I'm asking myself, and a question that I'm going to vocalize to you guys, and I'm not going to give you an answer necessarily. How could we have made this final answer? How could we have made this exactly 3.711? What would have had to have been different in our problem to make that happen? I'm going to give you a hint. It would have had to have been related to the acceleration that we gave them in this problem. But this is essentially problem design in a nutshell. If you followed me to this point and you've worked this out, you'll understand that being able to create an Atwood machine problem like this means that you really understand Atwood machines. And if we go to the test and I give you either this style Atwood machine or I give you the table-based style, we have the pulley, right? We have one of these. Understanding all of the forces that are present, understanding how they relate to each other, how to make your sum of forces equation, how to draw the free body diagram, how to make something positive or negative, how to, like, when do we know to use M1 plus M2? All of these things factor into this giant problem that we just looked at. And if you're looking for extra practice, you could take this exact problem and you could have somebody solve for a mass. You could give them gravity and acceleration. Or you don't even have to give them gravity. You can say this problem occurs on Mars, and then they can go find that. Because in the real world, that's what you would do. You would fire up Google, you would ask Google how much mass is on Mars, and you would, or how much gravity is on Mars, and you would move on. And you could solve the problem for M1 or M2. Or even further, you could say M1 and M2 are the same. This system occurs on Mars, and it accelerates at this rate. That would actually be a really cool problem. It'd be kind of tricky, but be pretty authentic. Cool. Questions? Shoot me an email.